Hello F-sharp, and welcome back. We have one more step in our journey of writing a high-performance dictionary in F-sharp. Now, it's been a while since I've had a video, and the reason is because we had already beaten the performance of the .NET dictionary. It was brought to my attention, though, that there is another dictionary type coming to .NET in .NET 8 called the FrozenDictionary. Now, I really appreciate people pinging me about this online, saying, hey, Matthew, have you seen this? Have you checked it out? And initially, I wasn't going to look at it, but then I was like, you know what? Let's go ahead and see what the performance difference is and see if there's a gap. Well, what I've done and what you see on the screen right now is the benchmark of the .NET dictionary, FrozenDictionary, and our F-sharp static dict. And what I did is I took the last implementation that we had, and I've just kind of renamed it static dict because that's the scenario that was really motivating me to create this version of a dictionary. That and seeing some C++ talks and being inspired like, hey, dictionary is kind of a challenging data structure. I'm going to go ahead and give it a shot. And what we see is that the static dict, which is our F-sharp read-only dictionary, is faster than FrozenDictionary for integer keys in all cases, but it loses to the FrozenDictionary when the keys are strings. And this is very interesting. And I was like, oh, okay, that's interesting. I wonder how they are getting that additional performance. And I suspected it had something to do with what they were doing with string comparison or hashing, because that's an optimization that the .NET plain dictionary already has in it. It has special logic for if the key type is a string, where it will use some pointers and some special code for computing the hash code of strings. And so clearly, FrozenDictionary is doing something on top of that. And so I wanted to go and investigate, like, okay, where are they getting this additional performance from? So what I did is went into our benchmark, and you can clone this code and look at it all yourself. And I come down to where this benchmark was, and I wanted to look at, hey, this toFrozenDictionary method. Now, something that's important to know when using FrozenDictionary, if you want the code to spend extra time to optimize the read performance of the FrozenDictionary, you need to tell it that. It will not do this by default. By default, when it creates an instance of FrozenDictionary, it optimizes for the speed of construction. If you wanted to actually spend some time to make the read performance of the FrozenDictionary as fast as possible, you need to say, hey, optimize for reading equal to true. And so that's the first thing, because when I initially ran this, I wasn't aware of that. And then FrozenDictionary wasn't nearly as fast. I'm like, okay, I'm doing something wrong here. So it's an interesting API choice, but whatever, it is what it is. And so I F12 into that, and I see like, okay, we have this method toFrozenDictionary, and I scroll down and I see where it's choosing between, do I optimize for reading or do I optimize for construction? Now, in our case, we want to optimize for reading. We want something that's going to have as fast as possible read performance. So that's what I'm actually interested in looking at. And so now this takes us to the method choose implementation optimize for reading. Great. And then we immediately see that there's all this logic in here for looking at the type of the key and then choosing an instance of FrozenDictionary that is optimized for that scenario. So I'm going to go ahead and zoom out just a slight bit more. And we can see, hey, small comparable value type to FrozenDictionary. We have a version of FrozenDictionary that's optimized for int32s. We have some logic here saying like, hey, is the key type a type of string? And this is kind of what I suspected because we've already seen the .NET dictionary do something like this. And we have all these different optimizations that it can do. It has a version of FrozenDictionary which just uses the lengths of strings as the hash code. We have a version where, hey, it's a write justified case insensitive ASCII substring, a write justified case insensitive substring, and on and on and on. We have all these variations. And I'm like, oh my goodness, this is crazy. You know, one person's crazy is another person's great engineering. But what this is telling me is that, oh my goodness, they have so many different variations on Frozen Dictionary and that they're optimizing for. And we can see where it's doing this analysis. Right here, we go to analysis result, and up above it, we can see where all this code is for evaluating strings and which version of the Frozen Dictionary that it should use for the scenario. I looked at this and I was like, okay, I guess we're taking the gloves off. Up to this point, our version of the dictionary, and this is a completely legitimate thing that they are doing. Like, I'm not saying that this is like cheating or anything. I'm just saying like, okay, great. This kind of tells me where the line is as far as like how far are we willing to go with this engineering. Up to this point, we've been creating dictionaries that are a single class. And that single class would look at, hey, is this a value type for the key or a reference type for the key? Is that reference type a string? And then it would have some custom behavior based on that. What they are doing in the Frozen Dictionary is they defined an abstract class of Frozen Dictionary, and they've created all these variations on it. And so, first of all, we're going to use this technique as well. We are going to define an abstract class, which is a static dict, and then we're going to create different classes, which are variations on that. This is kind of funny because F# is not known as an object-oriented programming language. And it's a multi-paradigm programming language. It has the capability of doing inheritance and doing interfaces and all that kind of OO type of stuff. It's just typically not the first tool that we reach for solving a problem. It is completely capable of doing it though. So we're going to do that. We are going to create our abstract class, and we are going to have custom classes based on the different scenarios. So we will have one for an integer key type because they have that in here. We're going to have one for string. We're going to have one for reference types, and we're going to have one for value types. So we're going to have 4 different variations of our static dict dictionary. And when I looked at the string one, I'm like, okay, in theory, I could go and implement all of these different string variation optimizations, but I really didn't want to do that because that was going to be a lot of work. And so what I wanted to do is figure out, okay, which of these crazy string Frozen Dictionary versions is the one that they're using most of the time. And I will go and implement that optimization. So now we can compare Frozen Dictionary to static dict using similar optimizations to see like which one ends up being better. And the way I figured it out is I used Intel vTune. And Intel vTune is kind of the profiler you reach for after .trace or superluminal isn't able to give you the insight that you need. And there's a huge amount of data that you can go diving into as far as the performance of your code and how it's interacting with the CPU. But the important thing for me is I just want to say like, okay, which methods are you using for looking up the values in the dictionary? And that will tell me which string optimization I need to use. And what I'm seeing is write justified substring, write justified substring. We do see it creating an instance of the left justified substring class, but it's a very rare scenario. Far and away, it's using a write justified substring Frozen Dictionary for its implementation. And so I was like, okay, I will have my string static dict use this kind of write justified substring approach for computing hash codes for the strings, because that's really the main thing that's going on here. That's the main kind of optimization. So what does that look like? Well, let's go check out the code. So what that looks like for us when we implement that. So this is benchmarks. I want to come in here. And what you're seeing is I have, and what SOA stands for, we'll get to in a second, but I have this one function for creating a static dict, and then it will choose which variation it wants to create. Here, I have defined my static dict class, my abstract class, and it's saying, hey, they have to implement the getItem method, and this is what allows you to use the square bracket notation for looking up items inside of a dictionary. I wanted to kind of provide that API. I wasn't going to implement all the things that go into a dictionary. I just wanted to look at this one benchmark. So when I come to my string version of the static dict with this right justified substring optimization, this is what has changed. What has changed is I'm saying, hey, I'm going to have this function, which is string hash code. And what it does is it takes a pointer, and this is similar to what we were doing before, but now what's happening is that I'm immediately indexing that pointer to the far right side of the string. If we consider the left side of the string to be the very beginning and the right side to be the end of the string, I am moving that pointer all the way to the right side. And this hashing function is looking at 4 characters at a time. It's how it's doing its computation. And it's doing 4 moving left, another 4 moving left, and then doing additional computations. Now, this means that the last few characters at the beginning of the string may not be used when computing the hash code. And that's okay in this scenario, because what we saw is that it's the right side of the string that is actually uniquifying the string. It's not the left side. The left side has lots of repeated information, so it actually doesn't uniquify it very much in terms of creating a key and creating a hash code. So why are we okay with just ignoring those last few characters in the string? They don't provide much uniqueness, and it makes this loop very predictable for the CPU. And so it's very easy for it to say, like, hey, I see what you're doing. You're doing these 4 characters at a time, boom, 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 and then you're done. So very easy for the CPU to predict. And branch mispredictions are one of the things that we really want to avoid. And so we're wanting branch mispredictions to come down, because when we look at the code and we look at the branch mispredictions, we see that the FrozenDictionary has much better predictability than the static dict. They have 4,000 branch mispredictions. We have 7,000, 2,900 versus 6,000. So we are only looking at the part of the string that provides uniqueness. And we are making that code for computing the hash code highly predictable by not having kind of multiple loops for picking up different chunks of data at a time. Okay, what is the other optimization that we are going to use? Well, we are going to change the memory layout of our dictionary. Now, up till now, if we come back here and we look at the previous version, this is how we were laying out the data in the array that's our dictionary is storing its information as. Whereas I have this struct, and that struct is made up of 4 fields. One is the hash code, one is the next, it's a byte, one is the key, and one is the value. And then we have an array of these buckets. And this is a very common way to implement a dictionary. You will see this all over the place. And this is actually how the .NET dictionary, the .NET plain dictionary, implements its kind of backing store. At least it was the last time I looked at it. So this is very common. What does this actually look like in memory, though? That is a great question. So if we go and look at sharplab.io, what we can do is we can say, like, hey, let's create our bucket struct. We'll create an array of it. And then we can use the inspect.heap method to look at how is buckets actually laid out in memory. We can see how this thing is actually laid out on the heap. And we do that by saying, hey, run. And so it's going to give us a picture of what this data looks like on the heap. And what we see is that it has a header, it has a type handle, it has a length here, and then it has our buckets. So this is the first bucket. It's at index 0. And then we have our next bucket. It's at index 1, which is what we're seeing here. Our third bucket, which is at index 2. And our fourth bucket, which is at index 3. I'll come back here to the beginning. So what we're seeing is that we have our hash code, we have our next field, we have key, and we have value. And in this case, our bucket, the type, is an integer key and an integer value. And when we look at it, we say like, hey, hash code, the hash code field is an integer. It is taking up 4 bytes. The next field takes a single byte. The key field takes 4 bytes again, and the value field takes 4 bytes. This all makes sense. So but you might notice something. This whole space in the array is actually taking up 16 bytes, even though the data for our bucket is only 13 bytes. 4 for the hash code, 4 for the key, 4 for the value, and 1 for the next. That adds up to 13. But what you're seeing here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 bytes that this is taking up on the heap. Why is that? Data alignment. So what the .NET runtime does, and most languages that I am aware of, when you need to access data, having that data aligned to a certain byte in memory is going to determine whether it's really fast to retrieve or not. And so the .NET runtime and most languages will lay out your data so that values and fields are landing on cache lines in a nice location in a way that's easy for the CPU to index that data and retrieve it. And for example, like you don't want things kind of spilling over cache lines, and so that's why it does this data alignment stuff. Now, here's the problem. Our bucket only uses 13 bytes out of the 16 bytes it takes to store this, which means we are wasting 3 bytes worth of information per entry into this buckets array. That is incredibly wasteful. Now, most of the time, you probably don't care, but in our case, like, hey, we need this to go as fast as possible, and cache misses are one of the key things that we're wanting to avoid. And if your data is taking up more space than it really needs, it is by its very nature going to cause more cache misses than it would otherwise, because it's fatter, it's taking up more space. And so the probability of it causing something to be evicted or not being in memory is higher, which means that we are consuming more of the memory bandwidth between our caches and our main memory. This is very bad. Cache misses are incredibly expensive, typically on the order of 100 to 150 CPU cycles, which you think is not very long, but when you look at like the number of lookups that we are doing and the fact that we are looking at microseconds, like it is like 30 nanoseconds to look up some of these values and some of these benchmarks. And this is a 5 gigahertz machine. And that means, yeah, it is very, cache misses are very bad. So if I come back here, I see that we're being very wasteful with our data layout. Now, how do we address this? Well, the way we address this is using a struct of arrays memory layout. Now, what is that? Instead of having an array of structs, we're going to do something that's kind of like a transpose of that, where instead of doing that, we're going to have a struct, and the fields of that struct are going to be arrays for our information. And I can show you what that looks like in here. I'm going to go ahead and do it for ref because it's the most similar. And so now our data is going to be this struct, and I have a field which is keys, and that is an array of our key type. And I have values, which is an array of value. I have hash codes, which is an array of int, and I have nexts, which is an array of byte. By doing this transform, we are no longer wasting 3 bytes per entry. This will reduce our cache misses, which means our code will run faster. And this is a very common optimization inside of game engines and any high performance code. It also makes our data more conducive to using SIMD with, which we are not going to do here, but it's often a great way to unlock additional ways of performing optimization. And I want to give credit where credit is due. The idea for this, for me, came from the Odin programming language. Odin is one of these languages that's kind of like a C next language. It's not a replacement for C++. It's really meant as a replacement for C. And there are many incredible optimizations that happen inside of this language, and they have a hash table built into the language, and that hash table uses this same type of data layout, which is a struct of arrays is how it's laid out. And they have even crazier optimizations that you can't do in .NET. So this is where I got the inspiration from. Turns out FrozenDictionary does the same thing. So apparently Microsoft thinks that this is a good optimization as well in terms of laying out our data in such a way that we're not going to waste memory bandwidth and therefore incur additional cache misses. So when I take all of these optimizations together, what is the result? Well, we see that we are now faster than the FrozenDictionary in all scenarios. Faster for integers at 10 keys, 100 keys, 1,000 keys, 10,000 keys. We're faster, faster, faster. And then for strings, at 10 keys, we are significantly faster. For 100 keys, we're only a little bit faster. For 1,000 keys, we're a little bit faster. And then for 10,000 keys, we're dramatically faster. And what we see is that it's coming down to our code has fewer cache misses than the FrozenDictionary, and it has fewer branch mispredictions. Well, we see that we have more branch mispredictions than FrozenDictionaries when we have 1,000 keys in our string or 10,000. But the cache misses are the more expensive thing. And so the fact that our version has better cache behavior outweighs the fact that we have more mispredicted branches. So that should kind of key you into, if you have to choose between the two of these things, choose the branch misprediction. Don't pick the cache miss, because the cache miss is much more painful. So together, we are able to go faster than the FrozenDictionary.net. Now, what's the takeaway from this? My recommendation is you use FrozenDictionary. It is a great it's a great piece of engineering. Our version is not dramatically faster than FrozenDictionary, and Microsoft is going to support FrozenDictionary versus this static dict thing that I made. Like it's just me. So use FrozenDictionary. Make sure that you say, hey, optimize for the read performance, so you actually get that faster read performance. But the other thing I want you to take away is don't ever think that data structures are a settled science. We're like, hey, we have the solutions to like what the best versions of these data structures are. No, we don't. It's clear that like, hey, we can still improve on what already existed. So if you're ever in a place where like you're using someone else's version of a data structure and it's not giving you the performance that you need, don't think that you have an impossible task. Like, hey, you might be able to go and exploit some of your domain knowledge to create a version that is better optimized for your scenarios and be able to go even faster. So this was a challenge. I am not going to lie. This took me several days to figure out how to get faster than the FrozenDictionary. And so hats off to Microsoft for creating a great version of this data structure. So I'm going to be really excited to use it in my code. I love it when my code runs fast. And maybe they can steal some of the stuff that I've done and implement it in their code. I don't know. We'll see. Thank you very much for spending some time with me. I would love to hear from you. What are some other data structures that you think would be interesting to implement in F# and then optimize? I'm always looking for great ideas for things that people would be interested in. And data structures are a nice problem to do that with, because it kind of crosses a lot of boundaries, and everyone has to deal with data structures at some point. And so it's a great exercise for writing high performance versions of something. So please let me know down in the comments what you think would be some great data structures to optimize. Until next time, you have a wonderful day and keep writing that awesome code. Thank you very much.